In this video, we are going to be talking about how to balance chemical equations. So, why is it important to balance chemical equations? Well, the law of conservation of mass says that mass can never be created or destroyed. So as you can see in this unbalanced chemical reaction, we have one iron atom on both sides. So this one iron atom from the reactants is becoming the one iron atom from the products. But then we have two chlorine atoms from the reactant side and three on the product side. So where did this one come from? A chlorine atom can't just appear from nowhere. It had to have started on the reactant side. So we need to balance this chemical equation. In order to balance the chemical equation, we can change the coefficients. If there's no coefficient in front of a substance, that means that there's a 1. So this means we have one molecule of iron, one molecule of chlorine, and one molecule of iron 3 chloride. However, we can change those. The things we cannot change when we balance chemical reactions are the element themselves, and we cannot change the subscript. So if I put a 2 here, then that would mean I have 2 of these molecules. I have 2 Cl2s. So I really have 1, 2, 3, 4 chlorine atoms. Okay, so let's try and balance this. Here I've redrawn it, and notice the blanks are where we put the coefficients. So my irons look balanced. I have one iron on my reactant side and one on my product side, but I need to fix my chlorines. If I add, so on my reactant side, I currently have 2 chlorine atoms. And on my product side, I have 3 chlorine atoms. So I have fewer chlorine atoms on my reactant side. So I'm going to add another chlorine molecule onto my reactant side. So now I have 4 chlorine atoms on my reactant side and only 3 on my product side. So I'm going to add another one of my product molecules. So because I can't just add one chlorine atom, I can only add the entire product. So now I have 6 chlorine atoms on my product side, but only 4 on my reactant side. So I will add another chlorine molecule on my reactant side. And now notice I have 2, 4, 6 chlorine atoms on my reactant side, and 1, 2, 3, 4, 5, 6 chlorine atoms on my product side. So my chlorines are balanced. However, because I needed to add another product, I now have 2 iron atoms on my product side. So I'm going to need to add another iron atom on my reactant side. So now I have 2 irons, 6 chlorines, okay, so that's my reactant side, and then I have 2 irons and 6 chlorines, so I am balanced. So now what I need to do is input my coefficients. So I have 2 Fe's and 1, 2, 3 Cl2s, okay, so notice because of that 2, that implies that I have really 6 chlorine atoms, even though I just have 3 chlorine molecules. And then I have 1, 2 FeCl3. Okay. Even without these pictures, I'm going to show you one more way to do this. Without these pictures, I can create a chart to show how this is balanced. So I'll have my reactants on one side and my products on the other side. And then my elements, I have Fe and Cl. So on my reactant side, I have 2 Fe's. And on my product side, I have 3 Cl2s, so that's really 6 Cl's. So that's all the reactant side. And then on the product side, I have 2 Fe's. And I want you to notice we treat this coefficient with the distributive property. So it's 2 Fe's and then also 2 chlorines, but that would really be 2 times 3 because each one of these is really 3 chlorines. So that would be 6 chlorines on my product side as well. So I am balanced. I'm going to do one more example. So this time I'm just going to use the chart. So I have my reactants and I have my products. And then I have carbon, hydrogen, and oxygen. And I want you to notice that oxygen is alone in one scenario in this combustion reaction, which means oxygen is going to be the easiest to balance. So I'm going to save that for last. So initially I have 3 carbons on my reactant side, and I have 8 hydrogens on my reactant side, and I have 2 oxygens on my reactant side. On my product side, I have 2 hydrogens and 1 oxygen and 1 carbon and 2 more oxygens. Okay, so as you can see, nothing is actually balanced in this reaction. So what I'm going to do, I'm just going to change colors to show the next step. I'm going to start by balancing my carbons. You could start with carbon or hydrogen. Again, save oxygen for last because since it's alone, it'll be easiest to balance. So I have 3 carbons on my reactant side and only 1 on my product side. So I need to put a 3 here because that would make 3 carbons on my product side. But it also changes the amount of oxygens. So now I have 3 times the 2, so 6 oxygens there, but still plus that 1. So I'll have 7 oxygens. So 3, 4, 5, 6, 7. So now my carbons are balanced. So that's great. But hydrogen and oxygen is still not balanced. So now I'm going to try to balance my hydrogens. I have 8 hydrogens on my reactant side and 2 on my product side. So since this is H2, I know I need to put a 4 here because 4 times 2 will give me 8. So that would be 8 hydrogens. Okay, so my hydrogen is balanced. But now I've changed the number of oxygens. So this is 4 oxygens from the H2O and 6 oxygens from the CO2. So 4 plus 6 gives us 10 oxygens. So now I need to figure out what goes here. How can I make 10 oxygens also on my reactant side? Well, this is 2 oxygens right here. So if I put a 2 here, I really have 4 oxygens. I'm multiplying the coefficient times the subscript. So if I need to get to 10, I would need to put a 5 there. Because 5 times 2 gives us 10. And so now I am all balanced. So this is the correct balanced equation. Notice there's a blank here. That blank implies 1. If the coefficient is 1, you do not need a coefficient. You can leave it blank.